So let's start thinking about optimizing continuous delivery. On the whole, continuous delivery is about optimizing to get very fast feedback into our development process so that we can move quickly and learn more effectively. And keeping it fast is part of the game. This talk is really aimed at those people who already have got continuous delivery up and running, but are kind of starting to think about the next stages. How do you live with it and how do you keep it going? So the starting point is probably, what's the starting point? And to my mind, one of the things that sometimes people miss is what's the basis of a deployment pipeline. And my starting point, my minimum deployment pipeline is probably something like this. We're going to have version control of some kind. We're going to have a commit phase, which is focused on supporting the development teams and giving them very fast feedback on the nature of their changes. And then we're going to have an acceptance phase, which is about qualifying our changes to determine their releasability. A deployment pipeline goes from commit to releasable outcome. And last of all, we're going to have an ability to kind of deploy the system because we're going to have tested the deployment and the configuration and so on, so we can deploy the system maybe even to production. So this is kind of my minimum deployment pipeline. Probably we'd add more qualifications into the acceptance phase in a more complex project, so adding more kind of things that we might be interested in. We might be interested in security or performance or data migration. All of these things might be things that could qualify our ability to release, to determine the releasability of a change. And so we might want to add those kinds of things to our pipeline too. The next question that kind of crops up at this point, I suppose, is what's the scope of a deployment pipeline? So here's a system. How do we tell whether this system is releasable? What part of this system do we need to complete and get together in order to determine the releasability of this as a system? Well, it's all of it. In this case, we don't really know that this thing is complete and coherent and whole until we know that all of it works together. And so there's something about the scope of a deployment pipeline. If we're trying to get to a releasable outcome, then the correct scope for deployment pipeline is something that's independently deployable. An independently deployable unit of software is what we're trying to evaluate within a deployment pipeline. Now, some kinds of systems may be made up of several discrete, independently deployable units of software. And in a system like this, we could add more pieces or take some away, and it's still a system. But each of those pieces is independently deployable. And that has an impact on the way that we think about and apply deployment pipelines. So the idea of a deployment pipeline really is that it becomes the only route to production. We would like to be able to put all of our changes through our deployment pipeline so that we can evaluate them and determine the releasability of those changes. So all change to production flows through it. That means that it's important. It means that this is your route to production. And so if it breaks or goes slow, it's a big impact on your organization and your ability to develop at all, really, because this is the core of delivering feedback into the development process. So performance problems in the pipeline are important. And figuring out how to optimize to keep the feedback from the pipeline fast and timely is important too. So I'm going to spend the rest of my talk describing these different points at which pipeline problems might arise. We might have a slow commit stage, a slow acceptance stage, failing tests, intermittent tests, and we might make changes to the pipeline itself. And all of those may cause us problems as we live with this technology and getting it working. So let's look at each of these in a little in turn. So here's our deployment pipeline, here's our commit stage. And as I said very quickly at the start, this is primarily focused on answering the question from a developer's point of view is, does the code do what I think the code does? Here's a typical kind of steps in a commit stage. We're going to maybe compile some code if we've got to compile a language. We're going to run a bunch of unit tests, certainly. We maybe do some static analysis of some kind, and then we're going to build some installers, the things that we will deploy into production, our release candidates. So a jar file, a .NET assembly, a DLL, an executable, a Docker image, whatever our deployable unit of software is, that's the thing that we build out of the back of a commit stage. So ideally, we're looking from a commit stage for feedback in ideally under 5 minutes. We're looking for this to be very fast feedback in order to be able to support the development process. So what kinds of things do we need to think about to keep it fast and keep that feedback possible? I think the first thing to say is that this is the most valuable feedback cycle in the pipeline. This is the thing where you gain a lot by making this efficient in terms of the development process. This really is the primary developer supporting function of the pipeline. And so keeping this efficient is worthwhile investing in. So the first things that might go slowly, well, compilation, that's one of the steps. So make your builds efficient. Weirdly, things like build scripts are one of those places where we developers tend to sometimes take our brains out of gear and end up writing horrible, nasty spaghetti balls of mud instead of nicely well-factored, modular, efficient bits of code. Rewrite them, make them nice and modular and efficient. Try rewriting them and try speeding things up. Buy faster hardware. This is not a place to cut costs. I once worked in a trading environment and did some analysis on a large C++ build that we were trying to speed up, and came to the conclusion that there was a limited amount that we could do, which we did. But I also went to my boss with a bill for a very large set of hardware so that we could run these builds in memory rather than on disk. We could build C++ builds tend to be IO bound, so we put them from RAM disk to speed them up. Parallelize the build things in parallel, take advantage of the multi-core nature of modern processors, or even create a build farm in which you can build things on separate bits of hardware if possible or appropriate, but look to parallelizing the process to speed it up. Decompose your system into independent modules or services, each with its own pipeline. There's a problem with this, though. This is trickier than it looks. It sounds like the obvious answer, but dependency management is one of the genuinely hard problems in computer science. And microservices are no silver bullet. If you'd like to understand a little bit more what I talk about, I operate a YouTube channel called Continuous Delivery, and one of my more popular videos on that channel is about the problems with microservices. Not meaning that microservices are a bad idea, it's just that they are not what most people think. So if you're interested in learning more about that, take a look. But it's primarily this. It's about trying to manage the problems of dependency management. Independently deployable units are the scope of deployment. So if you are going to decompose your system, you need to be able to comfortable that they are independently deployable. That is, you don't get to test them together afterwards. So this can be a route of speeding things up though. Also look to modern build systems. Modern build systems are pretty good at several of these problems, introducing ideas like build caches, incremental builds, and parallelized builds. Gradle, Bazel, Buck are all examples of build systems that have features for different languages and at different levels of support for doing large builds very quickly. Bazel is the Google build, Buck is the Facebook build, both of which work very fast, very efficiently in heterogeneous multi-technology environments, building systems very quickly indeed. Try running the build from RAM disk. I mentioned this already. This is good for some kinds of technologies, particularly those that are disk bound. RAM disk still has a higher bandwidth than most SSDs, so certainly use SSDs rather than spinning rust disks if build performance is an issue. But RAM disks can give you a bit more of a step forward because they are less I/O bound. So this is an opportunity potentially to speed things up. The next part of the commit stage is testing, and the most obvious thing to do if the tests are too slow is to look to the tests themselves. Often tests are poorly written. In particular, tests written after the code tend to be too big, too complex, too tightly coupled to the code, and so inefficient. Better tests are written test first. You write the test first, and then they are generally more decoupled and usually faster to operate as well as a result. Mostly what you want from commit tests is that they are pure unit tests. They don't start the application because that's too slow. They don't write to disk. They don't write to a database. They don't use the network, and they fake external dependencies. That way you can run hundreds of thousands of tests in just a few minutes quite relatively easily. But if you do any of these things, you rapidly start to run into the limits of trying to get efficient builds. Be very grudging in your acceptance of any slow tests. I talk about the objectives of the commit stage being in two parts. One is fast feedback in under 5 minutes, and the other is a high level of confidence, roughly 80% confidence that if all of these tests pass, everything else is going to be good. If something gives you the 80% confidence but is slow to run, as long as it's not too slow, it may be useful, but it's got to pay for itself. It's got to be really important. It's got to pay for a really common cause of failures or something like that. I once worked on a large Java project, and we were using Spring in the days where the only way of configuring Spring was with an XML file. Spring, for non-Java people, is a technology that determines the relationships between the different parts of the code and kind of wires them together. The problem with Spring is it's a runtime technology in those days anyway. You don't find out that there's a typo in your XML until you try to execute that script at runtime, and then it fails with some usually cryptic and hard to debug error message. So we had a we had a build at the time where our commit stage took 4 minutes for building a very large complex system. And we, in parallel with that, we ran a 2-minute single test, which was our Spring test, to start up the Spring configurations and just check that they worked and that there weren't any obvious typos in them. It was horrible. It was expensive to run as a single test, but it gave us feedback that was useful. So be very wary of accepting slow tests. Don't just accept that tests are always slow. They are not. You can write very fast tests if you put your mind to it. Always think about efficiency when writing tests. I like to think in terms of chicken counting, 0 and many. So I will never have a test that, I don't like loops in tests at all very much, but if I do have to put a loop in a test, I'm probably going to loop no more than 3 times at max. I'm certainly not going to loop hundreds or thousands of times ever in a test. If it can do 0, 1 and many, that's all code ever does. So that's good enough to be able to test. Use mocks and stubs to isolate the focus of the test so that you can evaluate the code that you're working on without bringing in lots of slow dependencies that slow you down. There are some downsides to mocks, and you have to be careful to do those well, but it's still a good technique for isolating the stuff that you're trying to focus on. Periodically, as a team, a more sort of pragmatic thing is do a run of your commit tests and sort the results by how long each test took to run. And then have a day with the team where you select the slowest tests in order of slowness and try and rewrite them to be more efficient. Try and come up with a better way of testing the same idea that's more efficient. And just go through and just periodically do that, and that tends to weed out the worst culprits. In general, as a rule of thumb, I'd be very, very suspicious of any test case in your commit stage, apart from the kinds of things that we just, the exceptional ones that we just talked about, like the spring test. The normal run of the mill that takes more than 2 seconds. That's probably too slow if it's doing that. Most tests should be running in milliseconds for most modern technologies. Run tests in parallel. This is difficult if your test isolation is poor, so don't have poor test isolation. Improve the design of your tests and your code so test isolation is good and that you can run them in parallel. This is good for the code as well as being good for your ability to parallelize the tests. So fix that problem. As a last resort, if there are slow, problematic tests, but tests that you think are important to evaluate the system, consider moving them out to a later stage in the pipeline. I once did some work, I've just mentioned it, the big C++ project. I was working in a trading company. We had when I started working with them, they had their biggest problem was a large C++ build that took 9.5 hours to do the build and to run all the tests. So they did overnight builds. So what we did, one of the things that we did lots of things to speed it up, all of the things that I've talked about so far. But one of the other things that we did was that we just arbitrarily sorted the tests, and we said that any test that ran in under 2 seconds, we counted as a unit test. Anything that took longer than 2 seconds, we counted as an acceptance test, which runs at a slower, on a slower pace. And that gave us a way of making progress and giving fast feedback, timely feedback into the development process. So it's a bit of a hack. It's a bit of a, it's not an ideal situation to be in, but pragmatically it can be a useful way forwards. The analysis tests can sometimes be slow. They can give really valuable feedback, but you need to be sure that it's valuable if they are slow. So it needs to pay for itself. If your analysis tests are slow and don't catch bugs, then don't do them. That there's no virtue in running tests that don't find bugs for you. As a last resort, you can move analysis out of this stage, but there are often types of analysis that you can run that are very quick. So one of my preferences in terms of analysis tools, at a minimum, as part of the commit stage, I like tests that kind of assert my coding standards. So that if I then commit a change that doesn't meet my coding standards, the change is rejected by the commit stage. And you can do that with tools like lint or find bugs or check style in the Java world, those sorts of tools, kind of lightweight analysis tools. The more complex things that do a deep analysis of your code, Coverity or those sorts of, or Sonar, those sorts of tools, may be too slow, and you may need to, if you value the output of those, you may need to move them out of the commit stage. As a last resort, give up and move analysis out of the pipeline. You know, you can achieve the result. You can run analysis periodically and get useful information from it without it necessarily stopping you from releasing a change. You know, you can cure the problems that analysis finds by better discipline in other parts of the process if you find it impossible to be able to get this into the pipeline and get feedback in a timely manner. The next thing in the commit stage that we're interested in doing is that we want to create release. We're going to build installers that are our release candidates, the assembly of bits and bytes that we will deploy into production. And so that's what we're aiming to create as a result of a successful commit stage. So the successful commit stage produces one of these deployable things. For some technologies, this is difficult to achieve. some kinds of technologies, building those installers might be problematic. If creating it, so I'm thinking of things like embedded devices or FPGAs or those sorts of things, where just the process of generating the deployable thing, in this case, burnt silicon, is costly. It's gonna slow you down. So if creating installers is slow, then consider moving it out of the commit stage. This is a fairly decent candidate for moving it out of the commit stage to optimize the commit stage itself, because the installers are not really the place where you're going to find a lot of problems. At this point, if you've got to a bunch of tested working code that you've evaluated with all of your commit tests, it's very unlikely that you won't be able to package that into something deployable. That's not a place that commonly finds errors. So it's okay to kind of move this out, and so report back that the commit stage was successful before you've started or at least finished building the installers. The downside of this is that you're still adding delays into the pipeline overall, but it still allows you to optimize the fast cycle, the commit cycle. Excuse me.
Bless you.
Thank you. Part of the process of keeping this going is the continuous integration process, and keeping the pipeline flowing is as much a human activity as it is a technological one. So some advice for keeping that working. So always run commit tests locally before committing, at least those in the area of the code in which you're working. So just to be sure, have a reasonable amount of confidence that you're not going to introduce a breakage to the deployment pipeline. Sit and wait for the results of the commit build. This is why I recommend that we optimize for 5 minutes, because what we're trying to do is that we're trying to encourage developers to work in small steps, and for each step to give them confidence that they can safely move on to new work if the commit build says everything's okay. So what we want is that the developers to be there waiting in case they do introduce a breakage, and then they can recover that change very quickly. So don't go home, don't go to lunch, don't go to a meeting, don't go to make coffee while the commit build's running. Sit there, wait for the result, and then do those things. If you do introduce a failure at this point, then start a clock. Sort of try and adopt the discipline that you're going to commit something new within 10 minutes. You're going to commit something that's going to fix the problem, or you're going to revert the commit that introduced the problem within 10 minutes. If you're working in small steps, you can usually identify the problem and understand the fix very quickly. But even if you're not reverting in 10 minutes, it keeps the pipeline open as a channel to production for the rest of the team. If a teammate has broken the first or the second rule here, if a teammate's gone home or gone to lunch, revert their change for them, because you need to keep the pipeline open. You can tell them later that you helped them out by reverting their change, and in future they should be a little bit more careful about following the second rule, but don't be precious about it. Revert the change, keep the pipeline open, keep the development, keep the feedback going. If somebody else notices that you broke the build before you noticed, a build sin, and you should be punished for build sins. I've worked in teams where we had to wear a silly hat until the next person committed a build sin, and one of my teams, we had a sin jar. So you had a jar with a slot in the top, and you had to put £1 in the jar every time anybody committed a build sin, and then periodically we go and take the jar to the pub and celebrate build sins in the pub. Once the commit stage passes, you move on to your next task, but you keep an eye on the rest of the deployment pipeline to make sure that everything else is good. Monitoring the progress of your change throughout the pipeline. And the rest of these rules apply if a later stage in the pipeline fails with a failing test, then start the clock. You've got 10 minutes to check something. If somebody else notices that you broke the build in a later stage before you do, it's a sin, and you have to follow the punishment, whatever that might be for the team. Continuous delivery is about optimizing your process to keep the software always in a releasable state. That means pipeline failures are top priority. What I've just described is this is kind of the human CI version. We're going to commit a change to the version control system. That's going to trigger a build management system of some kind to evaluate the tests. And this is human CI, really. There's another approach, which is gated, where we can kind of alleviate some of these things a little bit, but I don't think it eliminates the rules that I just gave you. So in this model, you logically commit to the commit stage rather than to the version control system. The commit stage runs all of its tests, and only if all of those tests pass are the changes then merged into the version control system. And that has some advantages for larger teams and for teams that are less familiar with continuous integration. It can help reinforce the discipline a little bit. The downside of this is that it's a little bit more complex to set up, not a lot, but a bit more, but it's quite hard to do it in a way where there are certain kinds of errors. If a merge fails post-commit, so commit passes, but your merge for some bizarre reason fails into the version control system, that's quite a difficult error to report in a way that people will understand. So it's a little bit tricky in terms of supporting larger teams, but it's worth thinking about. So in summary, the performance of the commit stage is probably the most important things to get right. Teams with fast commit stages keep the build green. It's one of the key tools to allow you to stay on top of failing tests. It's kind of an obvious reason. Just think for a moment what it means if you've got an overnight build, which is pretty good by industry standards if you've got an overnight build. But if you've got an overnight build, then I as a developer commit a change, introducing a defect, and I don't find out until the following day that I broke something, and I immediately know what's wrong, and I immediately commit a change to fix it, then I don't find out the build is now broken for a day, and I don't find out whether everything's okay until the following day. So the build is broken for half the time for every given change. So a day is too long, so we need to bring the cycle down. We need to bring the cycle, which is one of the reasons why I talk about these very short cycles, to be able to stay on top and keep the build green so that we're getting the clearest signal about the releasability of our code. So commit stage performance is an important thing. It's worth investing in. Next on my list are slow acceptance tests. So here's the acceptance test. Generally, this is the pattern for acceptance tests. We're going to configure the environment in some way. We're going to deploy a release candidate. We're going to run a smoke test or a health check to make sure that the release candidate is up and running and ready for use. And then we're going to run the acceptance tests. The first three are really just describing what I think are the steps in deployment. The last one is, so we'll see those again. We'll reuse those. Ideal feedback cycle for this stage is kind of under 45 minutes. Ideally, what we're shooting for, as far as practical, is to get a clear signal. Is my change releasable in under an hour? That's good. If you can do under an hour or better, you're in a very good place. Slower than that, it's tougher to stay on top of test failures. So first of all, configuring the environment. Depending on the nature of the environment, this can be easy or complex. But if it is complex, one of the things to think about is to think about the change layers. You're probably not upgrading, you're not deploying changes to the version of your operating system as frequently as you are deploying changes to the application. So you could kind of optimize so that you reuse the operating system part of the deployment, and you don't have to redeploy that every single time. That's one way forwards. You layer the configuration of your system so that you can kind of decide which layer to do. Actually, modern deployment systems, things like Docker, do this internally on your behalf. They have a layered version control system, so they can help with that to some degree. Consider where you do have expensive parts of the production process for building releasable things. consider generating pre-baked templates, so you have a pool of things available. So going back to my example of the operating system, if you've got a particular operating system, it's configured in a particular way, then maybe you just generate in the background somewhere else outside of the scope of the pipeline, a continual process that's just building those things. So you've always got some available, and then you can just pull one off from the pile of images, and then configure that, and that might give you a route to optimizing things. Containers like Docker help with several of these ideas, and it's one of the ways in which they add value. So that can certainly help. Successful deployment ends with a running working system. So for efficiency, we need to consider the time to deploy the system, the time to migrate any data so that it's useful, and the time to start the system up, and then the time it takes to validate that the system is up and running. And we'd like all of these things to be efficient. So time to deploy. Make sure that you are keeping the artifacts that you are deploying as lean as possible. Deploy the stuff that matters and don't carry around a lot of baggage. I did consultancy for a client in Silicon Valley a few years ago, and their deployed image of their system was 114 gigabytes. That's quite a lot of bytes just to ship around a network. When we looked into it, 112 gigabytes of those was a block of production test data, which nobody needed except in one particular environment. So we took that out and immediately sped the whole deployment process up considerably. Packaging strategy can make a big difference. Trying to figure the way in which we organize our release candidates and package it to support deployment can make a big difference to the performance of our deployment. Network infrastructure constraints and so on can make a difference, particularly if you're deploying to organizations or teams or parts of the world that have a lower, a poorer network infrastructure. That can be an issue. So think about that, and think about modeling that or testing it in some circumstances, certainly, but you probably don't want to be hitting those kinds of constraints within your own networks. I have a client at the moment who is struggling with a remote team. They have a WAN bandwidth of 50 megabits per second between a team in America and a team in another part of the world, and that's shared between 200 odd people. That's not great in terms of infrastructure, and is slowing them down and is costly as a result. Minimize data sets where you can. Try not to be shipping large data sets around with your code in test environments, certainly, but in general, that's kind of good advice. Think about better modularization and so independently deployable services. As I said earlier, this is trickier than it looks to get right, but it can be useful. And certainly in terms of the thinking about starting up the system, organizing things so you can start services up in parallel. What's very common with distributed systems is that there's some kind of startup ordering. You can't start service B until service A is running. That's not a good place to be. So you put into the design of service A and B that you can start them in parallel with each other, and whichever comes up first, if it needs to, it will wait the other before being ready for use. But you can do the deployment in parallel. Invest in optimizing the code executed during startup. Make it genuinely efficient. Fast startup is useful to have. It's good. If your software takes, I've seen software that can take hours to start up. That's not good. That's not a good use of time or effort. There needs to be a very strong reason why that's the case, if it is the case. Consider better modularization, independently deployable services. We've talked about that already. It's a good strategy, but not as easy as it sounds. There's a common cycle with acceptance tests that's kind of worth considering. Start writing by acceptance tests and run them all sequentially, and then as the number of tests increases, the time to deliver feedback increases. So teams then will start to parallel the acceptance test tactically. They usually buy another server and they'll just artificially divide those up. Teams move to a strategic parallelization later on as the number of servers grows. And so test isolation is useful to think about. And if you build that in from day one, that's at the point at which you need to start adding more hardware and parallelizing more. It's going to be easier to be able to do that when you started thinking about this. Test avoidance is a fairly common strategy. So trying to pick which tests to run for a given change. It is difficult to do well. And if I'm honest, I have never found a way of doing it well that was as fast as just running all of the tests. So be careful that you don't spend too much time calculating which tests to avoid when you could just be running tests. Scaling up, typically this is the kind of model that I have in my head. Maybe we'll have a release candidate that's identified. Our acceptance test environment comes free. It pulls it down, deploys it to a shared acceptance test environment, and then we spin off a bunch of test hosts that will run tests in that shared environment in parallel. This way we're sharing out the startup costs of our release candidate in that shared test environment amongst all of these tests. And so each test, on average now is more efficient as a result than if it started the system up for itself. Then you kind of get to this kind of thing. This is a real picture of dynamic acceptance test allocation, where we're analyzing tests depending on whether they can run in parallel with each other or not, and allocating those to a test grid at runtime as the tests come free. And you get into those sorts of things when you start getting to optimizing these kinds of processes. The efficiency of the feedback cycle is central to the ability of the team to keep the tests passing. And passing tests are the signal that we use to design software. So it's crucial to our ability to maintain performance. My general advice is that we're looking for 5 minutes feedback from the commit stage and under an hour feedback for the whole pipeline to determine the releasability of our code. That's tough. That's a difficult ask. I recognize that, but it is possible on surprisingly massive scales. Continuous delivery is all about keeping the build in a releasable state. That's my elevator pitch for continuous delivery. Work so your software is always in a releasable state. And so the pipeline is our tool that gives us that feedback. This means that a failing test is the signal that we use to say that our change is not releasable. That means two things. We want that feedback really fast, as I've discussed, but also we want to be able to trust the tests. So if a test fails, we want to be comfortable in just rejecting that change. This is not going into production because this one test failed. That's the signal that we're trying to work. So that means then that we must prioritize failing tests. They're important to get back to a position of being releasable. They are what determine the releasability of our changes.
A few minutes to finish them, okay?
Sorry?
Just a few minutes to wrap up.
Yeah. Intermittent tests are a pain. Too many teams live with intermittent tests. They're carrying this heavy load all of the time. Some continuous integration systems do a thing that I think is terrible, which is they give you the option to say, if a test fails, run it 2 or 3 times until it passes. Well, what does that mean? If it failed one time and passed another, why do you trust the time when it passes rather than the time when it fails? One of them is lying to you. The safest one to assume that it's lying to you is when it's passing, not when it's failing. So I think we should take failing tests seriously. If a test fails, it's telling us something. It might be a badly written test, so go and rewrite the test and make it better. But don't automatically assume that if you ran it again and it passed, everything's good, because it's probably not. Don't live with intermittent tests. Solve the problem. Figure out why they're intermittent. It's useful sometimes to track the intermittency. You can do that by just kind of monitoring the history of the last few test runs, but treat intermittent tests as failing tests. The last resort, if you can't fix it, you've got to ask the question, is this test really delivering any value? And maybe delete it if it's genuinely intermittent and you can't figure it out. We got to the stage where I'm building a fairly sophisticated system with intermittent tests that we got over the easy things, which were badly written tests after a while, and got to fix those quite quickly. But then we'd have a knob of intermittent tests, and every time we dug in, they were always highlighting a real, subtle, difficult, but true problem with our system. So fix them. The commonest causes of intermittent tests are race conditions, poor test isolation, poorly designed test cases, and sometimes it's something serious. So prioritize fixing intermittent tests as part of the development process. The last of my categories of problem are pipeline changes themselves. The deployment pipeline is a strategic resource. It's our route to production. Consider, if you're in a large organization, maybe start thinking about service level agreements for your pipeline, maybe even redundancy, clustering, highly available systems, and those kinds of ideas to keep the pipeline going. The pipeline is a complex system in its own right. So we want to apply the same kinds of techniques that we would for any other pipeline system. Think about versioning it and your tools. It's one of my criticisms of deployment pipeline tooling in the past is that often it was difficult to version control, which is ridiculous. It's got better since then. Consider writing test cases for some of the pipeline behaviors. And yes, in the past, I have had built deployment pipelines to create deployment pipelines. It sounds like overkill, but it's useful in some circumstances. Think about blue-green deployment strategies for pipeline changes, so it's easy to step back if you make a mistake. Use infrastructure as code for all pipeline hosts so that you can quickly create new copies, new versions of any of your pipeline hosts. Your pipeline make your pipeline the only route to production. Continuous delivery is a competitive advantage. It allows us to carry out experiments, learn quickly, evaluate ideas efficiently, and the pipeline then is crucial to our ability to deliver on that. Thank you. That's the end of my talk.